Tuning. How do I choose Ki, Kp and Kd? Okay. Algebra. So far, I think in the tutorials you guys are probably now quite familiar with the idea that second order transfer function, express it in a standard form, and I can work out omega n and zeta and rise time and settling time and all those other definitions that we've given you. So, equally, if you're given a performance specification, I want a rise time of not more than 10 seconds or whatever it might be, you can work from those definitions back to a transfer function that will give you the performance you want with numbers in it. And if you've got a real system with variables in it, you can match the two by comparing coefficients. So you can build the perfect transfer function based on your performance requirements. You've got the actual transfer function, which hopefully has got some variability in it. You can choose Ki, Kp, Kd, and all you need to do is make the two the same by comparing coefficients. There are other ways to do it, which I'll get onto starting next week, using what we call pole placement. You may have come across some pole placement techniques in maths, maybe last year, but we'll have a look at that. And this is all to do with mapping the position of the roots of the equation in the transfer function. Because the transfer function really is just a representation of a differential equation. If we understand the roots of that equation, we can also define performance. Okay. That's next week, don't worry about it. Well, not yet anyway. Or we can use empirical methods. What do I mean by empirical?
Based on observation?
Based on observation, thank you. That's probably a better definition than I would have come up with, in fact. There are methods for designing controllers that are based on observation, rather than algebra, rather than those sorts of simulation tools. If you think about it, we have to have something, because certainly number one, and probably number two, those methods are reliant on us having a system model that is pretty accurate. Okay, when we go out and we're thinking of that position control system, one of the big numbers in there was the moment of inertia, and I started to talk about a radio telescope. The quality of your model exactly depends on how accurate you know that number. So, it was built 70 years ago. Does anybody actually really know the moment of inertia of that structure right now? It's got 70 years worth of paint on it, 70 years worth of rust in it, and probably lots of other modifications. So very, very often it's difficult for us to establish a precise system model. There are ways of doing it, there are ways of identifying the system transfer function, but we cannot rely on always knowing the precise system model. And that's where these algebraic methods start to fall apart. Okay. If we've got a good system model, a precise system model, then the algebraic model is great. It's dead easy. Because we can do algebra, we can do it sitting at the desk, say, okay, set the controller to these values. But we sometimes simply don't know the coefficients. And the same problem actually exists with pole placement, because that's also dependent on the transfer function. Empirical methods based on observation do not allow you to produce precise specification of output. If you got your algebra right, you can choose the controller gains that will give you, I must have 11% overshoot, for example, or some precise number, and you can work to that. The empirical methods let us get, assuming we start out with a reasonably well-behaved system, these empirical methods allow us to produce the controller gains that will give a reasonably well-behaved performance. The most famous of them is a thing called Ziegler-Nichols, and a lot of these are based to a large extent on observation and experimental practice, and they give a pretty good result for a well-behaved system. Okay. But it only works for certain types of system, but thankfully most well-behaved process control, particularly process type systems, it works with them. So how do we do it? There's the standard industry approach, okay, which is you're in your big factory, I don't know what you're making cakes, and you've got all this process control going on, and something's not working, so you need to set up a new controller. What you do is you go to the little office under the stairs where there's this cranky old man with a white coat, and you drag him out and say, fix that for us. And he'll go to his 3-term controller and do a bit of twiddling and then walk away back into his cupboard. And everybody would look at him and say, these control engineers are a bit weird. He's back in his cupboard, that's okay. And what you find is lots of industry, there's always a bloke like that. And he's the one, or she is the one they drag out to sort out these controllers. What they're actually doing is more akin to a cooking recipe rather than the algebra you guys have been doing so far. Okay. And this is how you do it. You've got a 3-term controller in the loop controlling your system. Let's say it's that position control thing. Okay? And I've set all the gains to 0, so not much is happening. And I will increase the proportional gain a little bit at a time. With this kind of system, if you increase it far enough, you can get the system into a sustained oscillation where it just keeps wobbling and it doesn't decay. In other words, we've managed to get it so that zeta equals 0 just by winding up Kp. And you write it down and you call it the ultimate gain, because it's the gain at which it just keeps oscillating. You also measure that the period of that oscillation. Okay, so I've got into this constant oscillation and I measure the period and hence the frequency of that oscillation, and then you look up your cookbook. And we've measured Ku, which is the ultimate gain. We've measured Tu, which is the period of that oscillation, and depending which recipe you prefer, you set your controller gains to these numbers. Okay. These are expressed, by the way, you'll see that I've got Ti and Td here. Lots of people describe 3-term controllers. The Kp is always the same, but it describes the integral and the derivative terms in terms of time. You can see the relationship. Integral time is Kp upon Ki, derivative time is Kp upon Kd. And you look up the recipe book. And it will give you, so long as the system is reasonably well behaved, it will give you a reasonably good result. That's the classic Ziegler-Nichols one at the top. So you set your gain to 0.6 of the ultimate gain. You set the Ti term to half of the period of the sustained oscillation, in other words a higher frequency, sorry that's time, a lower frequency, and you set the derivative control also based on the period of that oscillation. If you don't like that one, you can try a different recipe. All of these make perfectly edible biscuits, but you just have to choose which one you prefer. And then down here I've put a couple with a little bit more description about them. If you're prepared to put up with a little bit of overshoot, then you can use this recipe and it'll give you a very well behaved reasonably fast responding system at the cost of a little bit of overshoot. If you can't accept that, then this recipe down here will give you as good a performance as it can with zero overshoot. Okay, so the empirical methods are really very useful because you can set things up so long as those things that you're trying to control are reasonably well behaved. You can set them up with these empirical tools. Otherwise, you can finish this module and know exactly how to do it algebraically or exactly how to do it using pole placement, which is essentially an algebraic technique. I'm going to ask you a car question again. Who's driven a car with cruise control? Yep. Who's driven more than one car, preferably from different manufacturers, with cruise control? Do they feel the same? Next time you get the opportunity, they don't.
No.
You've tried it.
Yeah.
What were the makes of vehicles? All sorts.
Yeah, all sorts.
All
They're
sorts.
all different.
They're all different. Okay. I drive a VW. My wife drives a Ford. They've both got cruise control. They both behave completely differently. Okay. Because whoever set up the PID algorithms inside those things had a different idea about what the best performance is, and you've probably found the same. Okay. So another thing that you've got to take on board with all this control stuff is there is no single right answer. And if you take two systems that are supposed to do the same thing, you may find that Ford on the one hand and VW on the other have got different ideas about what the right answer is. So they will choose different values for their controller terms to give them the response they want. They are both correct. Okay? So it is a discipline where you'll come across lots and lots of right answers. Equally, there's lots and lots of wrong ones, but there's a range of behaviour that can be defined as right. In the same way, a couple of weeks back we were talking about things like settling time, and I said, you know, there are various definitions for settling time. So in a sense, it doesn't matter what's right. What matters is that you can make it do what you want.